Hi, everyone. Okay, so today's lesson is going to be on section 5.4, which is dividing polynomials. Our learning objectives for today are the following: being able to divide monomials, so just one term, being able to divide a polynomial, multiple terms, by a monomial, being able to divide polynomials using long division, being able to divide polynomial functions, so same exact process, but now we're in function notation. And then finally, we'll touch upon using both the remainder and factor theorems. Let's jump into it. So our first objective, dividing monomials by one another. At this point in the course, we're very familiar with our properties of exponents, how to multiply exponents that have the same base. We add the exponents, how to divide exponents or exponential terms that have the same base. We subtract the exponents. And then there are a few other properties. But now we'll divide monomials by other monomials, and then eventually we'll get into future objectives where we involve multiple terms. So let's tackle this by using some concrete examples. We have two monomials divided by one another. I'm going to put it in fraction form so you can really get a sense of utilizing our properties of exponents here. Probably see Suki just wanting to be part of the party today. Okay, so the first thing that we can take care of are our coefficients. -6 goes into 54, -9 times. And now let's use our properties of exponents with our a value. When we divide exponential terms that have the same base, we subtract their exponents from one another. A is the same as a to the first power. So 2 minus 1 gives us a. Or 2 minus 1 gives us 1, and a to the first is the same as a. And then let's look at our b's. We have 3 minus 5 gives us -2. Now we don't want any negative exponents here, and what's another rule that we learned? Well, off to the side, I'll put a little side note. Anything to the negative power is not a negative number. It is simply 1 over the positive version. So if we're looking at x to the -1, we have 1 over x to the +1, also known as 1 over x. If we're looking at b to the -2, we have 1 over that positive version, 1 over b to the +2. So now knowing that, we can replace. And let's put all of these terms under fractions. So -9 as a fraction is -9 over 1. A as a fraction, a over 1. And then that b to the -2 is 1 over b squared. That way, we can fully simplify this result to just -9a all over b squared. And we are done. Yeah, I would say dividing monomials by one another, pretty straightforward process because we're technically just using our knowledge of properties of exponents. It gets slightly more complicated when we're dealing with multiple terms being divided by one another. That's where we utilize either long division or synthetic division, which I probably won't cover in this video, but I might make another video just comparing long division and synthetic division with one another. Synthetic division is just a short way of doing long division. Okay, so once we get familiar with this process and practiced it several times, whether it's on our homework, whether it's in that workbook, really enforcing your knowledge, not just with me, but on your own, then you will be able to move on to the next step. And when I say next step, more like next objective. Just keep in mind that when you are dividing a monomial by another monomial, you want to always make sure that your final result is fully simplified. Okay, let's do another problem together. We have 14x to the 7th, y to the 12th, all divided by 21, x to the 11th, y to the 6th. And I feel like my video keeps going up and down because this laptop is on my knees, so I'm going to move this, so give me a second. All right, much better. So, once again, let's all use the same colors, orange, blue, and pink. So orange is for our coefficients. We have blue we'll use for x this time, and then pink we'll use for y. Okay. Now 14 doesn't go into 21 perfectly, but what do we notice? We notice that they both share a factor of 7. So we can divide both by 7. 7 goes into 14 2 times, and 7 goes into 21 3 times. Now let's move on to our x. We have x to the 7 minus 11, which gives us -4. And I'll talk about how we can move that to the denominator very easily in a moment. And then finally, let's move on to y. We have y to the 12 minus 6 gives you +6. So since we know that x to the -4 is just 1 over that positive version, 1 over x to the 4th, what we can do is anytime you see a negative exponent, if it's in the numerator, all you have to do is make it positive and jump it down to the denominator. If the negative exponent is in the denominator, then it's just vice versa. You turn it positive and bring it up to the numerator. So our final result is just 2y to the 6th, all in the numerator, and then 3x to the +4, all in our denominator. Once again, I'll color code so you could really see how this all plays out. And that's it. We just completed example 2 together. All right, let's move on to our second objective for today, being able to now divide a polynomial by a monomial. And so now we're dealing with multiple terms in our numerator, and then we still have that one term in our denominator. This is just the general way of representing a polynomial being divided by a monomial. Okay, so let's do a quick warm-up problem. 3 over d plus x over d. Well, this is the same when you're adding fractions that have the same denominator. This is the same as 3 plus x over d, which technically our numerator is a polynomial. Our denominator is a monomial. Are you getting the gist? So what can we do? We can break up our polynomial into two separate monomials, and then we can go ahead and simplify from there. Okay, so let's look at example 3. Again, we have a polynomial divided by a monomial, but let's break it up into 2 separate fractions so that we're back to sort of like our objective 1. A monomial divided by a monomial, and then we have another monomial divided by a monomial. Once you get the hang of this, you don't have to write out this step. You can just do, okay, how many times does negative 3xy go into 18x to the third y, and how many times does negative 3xy go into negative 36xy squared? But because this is the first time that we're doing this together, I really want to make sure that you guys are understanding this. So now we're back to monomial divided by monomial. Take it step by step. This time I'm not going to color code. Negative 3 goes into 18, negative 6 times. Then x to the third divided by x. 3 minus 1 is 2, so x to the second. And then y divided by y, the y's cancel out. So we got our first result. Second one, we have a negative divided by a negative is a positive. So we have a plus. 3 goes into 36 12 times. X divided by x, that cancels out. And y squared divided by y, well, 2 minus 1 is 1, so we just get y. There we have it, our final answer in simplified form. If you wanted to utilize your commutative property and flip this to become 12y minus 6x squared, you can. Either answers would suffice. Okay. Objective 3. So we are going to be able to divide polynomials using long division. And so we're very familiar with long division, just dealing with numbers. I'll run through it with you as sort of a nice refresher, but then we're gonna eventually incorporate some variables. And so the first thing that we're looking at is we're looking at how many times does 25 go into 875? And just some quick vocabulary terms. Quotient, whenever it says find the quotient, you're pretty much solving for that answer. All right, this is simplified to what? Our remainder tells us, okay, what's left over? Maybe 25 does not go into 875 perfectly. And if it doesn't, our remainder is not going to be 0. But if it does, our remainder is 0. Our divisor is always the denominator of our fraction. It's telling us, okay, we're breaking up this larger number, aka our dividend, into how many equal pieces, into 25 equal pieces. Well, if we're able to divide it into 25 equal pieces, what's our final result going to be? What is our quotient going to be? Okay. So now let's jump into our example 4. We have x squared plus 9x plus 20, all divided by x plus 5. Notice how I always like to put it in fraction form first so that I can easily identify my dividend and my divisor. And so I believe the quotient was gray. Our remainder was green. Is our divisor red? Yeah, our divisor's red. And our dividend is yellow. And I'll label them again. So this is our divisor. And this was our dividend. So when we put it into our little long division, home, I always used to call this a little box, a little house, we have the following. Our divisor is on the outside. Our dividend is nice and protected in our home. Again, I'll do some color coding. And now we are good to go. So this may look a little complicated at first, but bear with me. We want to ask ourselves, first, take it separately. Don't just look at it as an x plus 5. Let's just look at it as an x right now. And so x times what number gives us x squared? Well, x times x gives us x squared. And now this is sort of like a process. Now we take this, we utilize our distributive property, and we put that result down here. X times x gives us x squared, just like we originally said. And then x times 5 gives us a plus 5x. That's what we are subtracting from our dividend to see what's left over to continue to pull out some more. So x squared minus x squared cancels out. And this is the mistake that most students make, so please don't forget about this negative chilling off to the side. We have 9x minus 5x, and that gives us 4x. This plus 20, we can just bring down. And now we're going to repeat the process all over again. X times what gives us 4x? That's just 4, so we have a plus 4. And 4 times x, just like we said, gives us that 4x, what we wanted. 4 times 5 gives us plus 20. Would you look at that? If we subtract this, everything will cancel out, and our remainder will be 0, which tells us that our quotient was in, I think, a gray color, is x plus 4. And once again, I'll label it. So therefore, our quotient equals x plus 4, and we are done. So we're going to look back at the dividends in our previous examples, right? We have our dividend here, and then we have our dividend here. The terms were written in descending order of degrees. This is very, very important. There were no missing degrees. After we go from a quadratic, we jump down to a linear, then we jump down to a constant. And so if we're looking at a polynomial that is missing a degree in between, like this one over here, quartic function jumps straight down to a quadratic, we're missing a cubic function here, then we need to insert in that cubic function in order to create a placeholder. We won't change the polynomial that we're looking at, we're manipulating it. If there is no cubic function, then we just have that leading coefficient be 0. That way it doesn't change it, it just puts it there as, once again, a placeholder. So very, very important. I see this on assessments all the time. Please do not forget to do this. If you do, you'll notice that you won't be able to solve the answer properly, and then you'll just have to go back and redo your work. So now knowing this, let's solve example 5 together. X to the 4th plus 0x to the 3rd, we're inserting in that placeholder, minus x squared plus 5x minus 6, all divided by x plus 2. We have our dividend. We have our divisor. We will be looking for our quotient. And then our remainder will be all the way at the bottom, and I'll highlight that in green in a moment. So let's go through. X times what gives you x to the 4th? X to the 3rd. x to the third times x to the fourth, x to the third plus 2x times 2 gives you a plus 2x to the third. That's why it's really important to have that placeholder there. So now we have a cubic term. We're going to bring everything else down. And we're going to repeat the process. X times what gives you negative 2x cubed. That's just negative 2x squared. Negative 2x squared times 2 gives you a negative 4x squared. Again, we're subtracting this so that that negative 2x cubed cancels out. And so we have positive 4x squared. So negative times a negative is a positive. Minus x squared is 3x squared. Bring everything else down. Repeat the process. We get x times 3x gives you your 3x squared. And then 3x times 2 gives you a plus 6x. Ahead and subtracting. Bringing the negative 6 down. Repeating our process. We have x times negative 1 gives you negative x. And then we have negative 1 times 2 gives you a negative 2. Subtract. And so we get our remainder to be negative 4. And we are done. Right? So what did we get our quotient to be? X to the third minus 2x squared plus 3x minus 1. If you wanted to find your result fully, including in that remainder, you can write it as your quotient and then you put in your remainder all over your divisor. Again, I'll color code this. This is our remainder, this is our divisor, and then we have this guy as our quotient. But on the exam, if they explicitly ask you just to evaluate what your quotient is, all you're doing is solving for this above. Okay. Let's try another example together. We have 8a to the third plus 27. Ooh, did I do something wrong? You want to put it in descending order. So you're missing a few placeholders here. We have 0 a to the second and a 0a. And then we have our 2a plus 3. Also can notice that, and I'll maybe touch upon that in a moment, this is a sum of cubes, right? So let's go ahead and start our long division. 2a times what gives you 8a cubed? We have 4a squared. And then we have 3 times 4a squared is a plus 12a squared. I'm going to go ahead and subtract. Bring down everything else and continue the process. 2a times negative 6a Use a different color. Gives us that negative 12a squared. And then we have a negative 18a. Subtract. First term cancels out. Now we're looking at positive 18a. Bring down that plus 27. 2a times 9 gives you 18a. And then 9 times 3 is the plus 27. Would you look at that? Our remainder ends up being 0. So what does this tell us? This tells us that our quotient is 4a squared minus 6a plus 9. Now, we could also look at it from that sum of cubes format. Maybe I'll put this as a side note. We have our sum of cubes. A cubed plus b cubed. This is the same as a plus b. Space, let me move this off. And then we have our a squared minus 2ab plus b squared. And I made a mistake. It should just be a squared minus ab plus 2b squared. So now knowing that, and why don't I put this in a different color? Light blue, that's better. How can we break this guy up into this form here? Well, what's our a? Our a is the cube root of 8a cubed, which is just 2a. And what's our b? That's the cube root of 27, which is 3. Ooh, 2a plus 3. So we can really break that up. Let's use orange. 8a cubed plus 27 is equal to 2a plus 3 in parentheses. Our a squared is just 4a squared. Watch this be the quotient. Minus our ab is minus 6a. Plus b squared is plus 9. So it's really good to know these special factoring tools, because then you really don't have to rely on longer systems all the time. Once you have this, what are we doing? We're dividing this all by our 2a plus 3. Well, then that cancels out and we're left with our quotient, aka what we got when we did our long division. And we're done. And I'll maybe show it to you. We divide this by 2a plus 3. So these cancel out, and then this is our quotient. Okay. Yay. All right. This is just a notes slide on really how to step-by-step go through our long division process, but we went through it together twice already. So this is just another example to really get in the hang of doing it. Once again, they label what your dividend, what your divisor, quotient, and remainder are. Finally, we're on to our fourth objective, which is being able to divide polynomial functions. And so same exact procedure, it's just now you're dealing with the division in function notation. You just want to keep in mind that anytime you're dealing with functions and you're dividing them by one another, you do not want the denominator to be equal to 0, because if it is, then we have an undefined value. So we're given these two functions, and we want to evaluate f divided by g. And then we also, our part B, once we find this, we want to figure out, okay, well, now that we have that, can we plug in -4 for our x value in order to get a numerical solution? So let's take care of our part A first. Let's substitute. We have x squared minus 5x minus 14, all divided by x plus 2. And you can use long division here, but what do we notice? Can we factor that numerator? This can be factored into x minus 7, x plus 2, right? All divided by x plus 2. Saves us a whole lot of time, because then the x plus 2's cancel out, and we're just simply left with x minus 7 as our result. Now, I'll use long division off on the bottom here. Feel free to fast forward this if you don't want to run through the whole process again. But just to convince you that our quotient is indeed x minus 7. So we get x, and x squared plus 2x, that's being subtracted. So we're looking at -7x, bring that -14 down. And then we have a -7. And then we have a -7x minus 14 when we subtract it. This all cancels out, so our remainder is 0. And then lo and behold, we get the same result. But just takes us an extra second. So that was our part A. Part B, we just want to evaluate this at -4. So if we know that our f divided by g of x is x minus 7, when we evaluate our x when our x equals -4, wherever you see an x, we're going to draw a little parentheses. And then inside those parentheses, I'll do some color coding so you can really see what we're doing. We're going to fill that parentheses with our -4 value. And then we'll solve. -4 minus 7 gives us -11. So our final results are f divided by g evaluated at -4 is simply -11. And we're done. Again, same exact concept, we're just dealing with function notation here. And this was just a blank slide in case we needed a little bit more room. So our final objective for this lesson is being able to use the remainder and factor theorem. Let's jump into the remainder theorem first, which we have shown below. It tells us that if the polynomial function, f of x, is divided by an x minus c, then our remainder is simply f of c. And we'll practice that with our concrete example on this next slide. So instead of using the whole long division and everything, we can clearly see that our c value here, when we're looking at this as our divisor, our c value is -2. That ends up being a remainder of this function. And so it's just a quick and easy way to identify that it is a remainder. So we're going to use the remainder theorem to find the remainder of this function when it's divided by our x plus 2. So x plus 2 is really like our x plus c in disguise, which tells us that our c value is -2. If we plug in -2 into our function, we'll end up spitting out -2 in parentheses to the third, plus 3 times -2, plus 19. That gives us a -8 minus 6, plus 19. And then we have -8 minus 6 is -14, plus 19. That gives us 5. I made a mistake. What mistake did I make? I did not make a mistake. I was just reading it wrong. I think I had like factor theorem glued into my head for a second. Okay, so what does this tell us? This tells us that when we divide our dividend by our divisor, x plus 2, what is our remainder? Our remainder ends up being +5. And again, a quick and easy way to find the remainder without utilizing our long division. If you're not convinced, we can do long division off here to the side to prove that that's the case. We got to put in a placeholder. And then we're dividing this by x plus 2. So we end up with x squared subtract -2x squared plus 3x plus 19. Then we have a -2x subtract, so we get 7x. And then we have a +7. Just gonna move this down a little bit. Move this up. And then we have 7x plus 14. So 19 minus 14 gives us a remainder of what we were looking for, 5. And there we have it. It's just, again, this takes a lot more time than just utilizing our remainder theorem. Plugging in our c value into our function and boom. If it spits out 0, then we know that this goes into our dividend perfectly. And that's what we'll observe when we learn about our factor theorem, which we are at. So our factor theorem, we have our formalized definition below here. And this tells us that if x minus c goes in perfectly, then our f of c is 0. And then that tells us that x minus c is a full-on factor of that polynomial function, dividend, when we're dealing with dividend divisor quotient. Okay, so we want to use the factor theorem here to determine if x minus 4 is indeed a factor of this cubic function. So how do we do that? Well, x minus 4 tells us that our c value is equal to 4 here. So if we plug in and evaluate our function at 4, if we get 0, then it is indeed a factor. 4 to the third is 64. And 64 minus 64, would you look at that? That gives us 0. Therefore, our f of c is equal to 0. So x minus 4 must be a factor of our polynomial f of x is equal to x to the third minus 64. And we're done. Very, very handy theorems, both the remainder and factor theorem. I don't normally see both of them on the final exam, but I usually see at least one, and it changes from year to year. All right, and I believe that was our last question from this section. I hope that this was helpful. Feel free to go back and rewind if I was going a little too fast, but I highly recommend trying out those additional workbook problems from this section, and then you can also go ahead and do your online homework. Let me know if you have any questions, and I hope you have a wonderful rest of your day. Take care.